episode. We're very happy to have Eugene Stanley from Boston University. He's the Warren Distinguished Professor there and has received an abundance of awards over his career. He's a member of the National Academy of Science, a fellow of the American Physical Society, a fellow of the American Association for the Advancement of Science, and has received lots of honors such as a Guggenheim Fellowship and the Boltzmann Medal. I won't go through all of them because it will take too long. We're very happy to have Gene here. He's going to be telling us about the physics of finance. In particular, he'll be posing the question, can physicists contribute to economics? Thank you, Gene.
Thank you. Thank you for coming down. Wait till afterwards. Better you do it now. Afterwards, you may not clap. So it's a pleasure to be back at Brown. I was here just a couple of weeks ago to honor a dear friend of mine, Mike Kostelis, on the occasion of his birthday number 75, which sounded very old to me when I was younger. Now it sounds actually young, because I'm older than 75. And it's great to be back here. I've always loved Brown. I wanted to teach here, actually. I didn't get the offer, but I ended up at MIT. And but I really like Brown. I like Providence, and I like physics. And you have a wonderful location here, a wonderful group of people. And I hope you can stay awake for the next 35 or 40 minutes while I try to tell you about some recent things we've been doing. We means my students, and I'll introduce them in a minute. So a natural question you always naturally would have is, can a physicist contribute to economics? And there's no simple formula, but the first and most important item for me is to get a partner and to respect him or her. Because, you know, economists are not physicists. They have different ideas. And when you collaborate with anyone in a different field, respect is, of course, we have politeness, but real respect and admiration is not always easy. So you have to really discipline yourself to respect them. Number two, collect data. Data are real. The rest, especially in economics, can often be fantasy. And we're fortunate we live in an era of big data. That means everything, every transaction of every stock is recorded. And if you're a little inventive, or if you have graduate students who are good at stealing things in the middle of the night, you can get any data you want to get. And then once you have the data, you ask a simple question: are the data telling us something? And if so, what? And how do you find out? You do the natural thing. You quantify whatever you found, and then you say, you've got a bunch of numbers, what do I do? Well, of course, economic numbers go all over the map, so you have to do something. So a normal thing to do is to aggregate. That means time average over a little period or whatever. And then, and this is the most difficult thing, you find different things. The price is the most obvious, but the volume of trades, the time between trades, the volatility, which just means the standard deviation of the fluctuation. Try to relate those things, and they maybe can or maybe cannot. And last, but perhaps not least, just last, make a theory. Economists often do the reverse. They start with a theory, and the theory can be very brilliant. Economists are well trained in mathematics. They can do theories so unbelievably difficult. I mean respectable, difficult to read. And an economics paper can often look like a math journal paper with all the usual things, propositions and lemmas and theorems and proofs and corollaries and on. So, but I like to put theory last. And I like to dedicate this to big data. And why to big data? Because I believe in data-driven discovery. What else would it be driven by? Of course, it could be driven by your imagination, but my imagination, like most people, is limited by the size of my brain, which has been alleged to be minuscule. So, so you make the theory. So I dedicate this to Google and big data, and anybody who wants to interact more, you're welcome to jump on the train. Only 39 minutes if you get the fast one. To Boston. I'll welcome you for lunch, for dinner, for a chat, for a coffee, or if you're just on the way to the airport, just come an hour early and we can meet. I like very much to meet people. I don't mind if you pick an odd time, unless it's 6 a.m. on Sunday morning. And but write me first an email and say when you want to come. Okay, time to move. It's the only busy slide, but I like to put, this is not a good place to stand. I like to put everything on one slide, then you can fall asleep. So a complicated title, but it's roughly the truth, is to quantify fluctuations on time scales that range from a millisecond to years. That's a big number of order of magnitude. I think it's 11 orders of magnitude or something. Using concepts of, I'd say critical phenomena, but anything that switches, phase transitions, critical phenomena. We have one of the world's expert here in the second row, Professor Kostelis, and we know that those concepts are fairly vague, and that's why they work so well. And the main challenge is that economics, what makes it difficult, is it's always switching. What goes up now comes down shortly, and what goes down comes up. So if you don't, it's like the weather in Boston. If you don't like the weather, wait till tomorrow. And a cynic would say, if you don't like the weather, wait 4 hours. So this is not my work. It's work by many people, and the ones in green are real economists who know economics, and the ones in not green are physics background people, and maybe you could be one of them. I don't have to be green. I should have made that both colors, green and purple. And if you want to read easy, I hope easy to read book, we're just finishing a book called Rise and Fall of the Business Firm with former postdoc Bulgarev, two real economists, that's why they're in green. And we hope it'll become a bestseller. At least we may sell one copy if I tell you about it. So the key message was enunciated by Isaac Newton when the tulip bubble burst in the South Seas, and he said something like, I can understand the moon, the stars, the motion of the planets, everything else, but I do not understand finance. And some people think that the big bubbles, like the South Sea bubble or whatever, are the ones we have to understand and control because they do all the damage. One of the things that we found, and others of course have also found, is that there are bubbles of all sizes and shapes, a little like critical point phenomena. Critical points have these big fluctuations that make critical opalescence, where the dimension of the fluctuation is comparable to the wavelength of light or something. And similarly, there are big bubbles, that we read about in the paper, but there are smaller bubbles and smaller all the way down. And the remarkable thing is they're all conforming to the same law, suggesting that whatever is going on, it's the same on all scales. Again, a little like phase transitions. Okay, so again, like phase transitions, we cannot predict the future, but we can quantify the risk. Risk just means standard deviation. So it's like saying we know the susceptibility, which is a measure of the correlation, but we don't know much else. And again, it's a little like earthquakes. We can't know when the next earthquake is. It could be in 2 minutes. Better be ready to duck under your chair. Or it could be in 2 years or two decades. Or tornadoes or heart attacks and so forth. So the thing that distinguishes us in physics, us means not just me and my group, but other physicists, a lot of physicists now work in this field, is what I call DDD, data-driven discovery. And what does that mean? It means you look at the data and see if they're telling us something. So you discover things by looking at data. That's quite different than most economists who discover things by looking at some theory and say, look, the theory predicts this. And then they may or may not look at the data. If they look and it agrees, they're happy. If it doesn't agree, they publish it anyway. It's a beautiful theory. And I like to call this switching without switches, because there's nothing making these switches. News, some can make a switch. Bad news, when Kennedy was shot, the markets went down. But the market may have gone down today and maybe nothing happened. So there's no switches, but things happen. Again, a little like phase transitions, because you probably all know that near a critical point, the system flips from one phase to another phase, but nothing's making it flip. There's no little Maxwell demons throwing on a magnetic field saying, time to switch, go up, no, down, up, down. No one's doing that, and the same in the stock market. It's just It's a miracle. In my opinion, it's a miracle, and it's fascinating. And it's a little bit sad to me, or actually I'm happy, that economists haven't taken the approach we take, because they left us something to do. And otherwise they would have done everything. It's nothing we do is terribly profound. We can make this thing work. Look at that. So now we move on. We don't have forever. And who's going to watch the time for me? You have a watch, a big watch. Oh, I have to look at the clock. Okay. When did I start? 4? 10 minutes already? Oh my God. I have to go a little faster. Okay. I believe in starting with data. So the red curve are real data on a stock average of the 500 largest stocks called Standard & Poor. You just average the largest stocks and plot the price on the y-axis. So today it's actually above 1,000 because it stopped before the year 2000. And we all know what happens. It goes up and goes down. It goes up and goes down. And then occasionally it takes a big jump. That's Black Monday, 19th of October in '87, when the market fell 25%. This is a log-log scale, so you have to translate over and see that's 25% in one day. And many people remember where they were. I was in a dinner with my guest, gave a colloquium, and he had money in the stock market, and all he did was keep looking at his device to see what the market was doing and crying. And the soup bowl, instead of getting more empty, got more full from all his tears. So he lost a ton of money, apparently. So we all know this. What we may not appreciate is that this, if you open any finance book, the #1 model is a Gaussian. And I think you know enough about Gaussian that that's a simple random walk where a drunk throws a coin every tick of the clock, and the drunk moves left if it's tails and right if it's heads. And he or she moves ahead. But notice there's none of this. No big drops. Now you could replace the random walk with a levy walk, but you still have problems. And there's also no time correlations. If there were time correlations, we could all get rich. Just find out what it is and then extrapolate. But there's nothing. So it's certainly no Black Mondays, 25% drop, and so forth. Okay. So now we go a little bit faster. The word return means if I invest a unit of currency, like a euro or a dollar, in something, what do I get back? That's called my return. And for a simple Gaussian, which we just looked at, the black curve, we all know the returns are plus or minus at most 5 standard deviations, and the units of this y-axis are standard deviations. So you see nothing more than 5 standard deviations, because exponential minus 5 squared is very, very small. In contrast, stock markets, that's not true. Many times it's within 5 standard deviations, but look, here's Black Monday, where it was 20 standard deviations up, and actually people don't talk about it, it was 20 standard deviations down, but people don't talk about it, but it was also 20 standard deviations up. So these are the real data, and nothing unusual to show you this, except that my retirement, and yours too probably, are invested by someone else, and they use a model, and the model they use are these Gaussians. So they miss all these big things. Now, fortunately, everything's symmetric, so if you miss the big one going down, you maybe catch up on the one going up, but still, I'm not comfortable that my retirement depends on this top curve and not on the real data. So the fact is that with your eye, with nothing else, and Mandelbrot trained me to use my eye, that returns are not Gaussian. Large events cluster, see boom, 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 bad news, and then nothing much for a while, and then a lot of bad news. Again, not like a random walk where there's no clustering. And what usually people don't talk about, but it's true, aftershocks means after a big event, there is more shocks, more big fluctuations, and they're correlated. That was elucidated by a Japanese named Omori and developed by some of the people in our group. That's not me, I hope. Is that me? No, it's you. Good. That's you. Oh, thank you. That's me. I had run out. And the aftershocks are also correlated. That means of an aftershock, there's aftershocks. So when I say aftershocks of an aftershock, you think power loss, because boom, 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 cascade. Okay, so that's enough with the background. Oh, sorry. Now, what do we do? Well, what does a physicist do if they don't know anything like me? You look at the data and you make the simplest possible plot. And since we all care about whether our money is going up or down, we may make a plot of, on the y-axis, the distribution. That means the number of times the stocks or the market or whatever fluctuates or has a return bigger than the x-axis. And naturally this goes down. These are 100 standard deviations, so it's 10 to the minus 7 almost, versus 1 standard deviation, which is 10 to the minus 1. So there's 6 orders of magnitude here, and 2 orders of magnitude on the x-axis. So the slope of this data is roughly 3. We discovered this in our group in the same way I'm showing it to you, by making a plot, and of course by doing lots of little fancy tests, which the referees force you to do, but anyone can look at this plot and say there's something there. But particularly relevant is the fact that the Gaussian doesn't do this. And even Mandelbrot doesn't do this. The great Mandelbrot did look at finance, but he was in love with Paul Levy, and Levy predicted a straight line, but with a totally different slope. Mandelbrot said it should be 1.7, and you can see the data don't conform to that. What this does look a lot like is the Gutenberg-Richter Law of Earthquakes. And what does the Gutenberg-Richter Law tell us? It tells us that a big bad earthquake, like Richter scale 7, is probably obeying similar physics to the everyday earthquakes. And that's relevant. So we can study in detail everyday earthquakes, because they're every day, lots of data. And then hopefully we're learning something about the big bad ones. And so similarly here, we can study every little fluctuation and hopefully learn something about the big bad ones. So that's what these 2 brilliant students did. They analyzed, for every stock, 200,000 data points, and they studied the 1,000 largest stocks, so they had 200 million data points. Why so many? Because these are, what do we say, 6 orders of magnitude down, so 1 in a million. So if you have events that are 1 in a million, you need obviously a lot more than a million points, which only have 1. So there are 200 million here. And these 2 people did very well. And the first one is very rich. He went to Goldman Sachs. He doesn't talk to me anymore. And the second one is very smart, but she married him. And it's not nice to say in this day and age, but they're living a good life. And I love them both. Okay, so this is not limited to price fluctuations. Other quantities like the trade size, that means how many stocks did you sell in a given trade. Because you don't buy a stock, 1 stock at a time. You buy 100 of this, 1,000 of that, and so forth. So if you plot the PDF of trade size, you again get a straight line with a different slope. And again, there's something here to emphasize that this is universal in the sense that different countries with different customs, and nothing could be more different than the French and the Americans, as we all know. But the data, the black dots for the French and the red squares for the Americans, more or less fall on the same slope. So this suggests that there's something about stock price fluctuations that's, use that fancy word, universal. Okay, but you don't make money just by knowing that bad things happen. As my son says, Dad, shit happens. We all know that. We're going to tell something useful. We want to know, what is shit going to happen tomorrow? And if so, I want to make some steps today. And so this is a time lag of the price of a stock on semi-log paper. And you see it's a straight line, so it's falling off exponentially. But the time constant is 4 minutes. So high-frequency trading can make a little money this way, but not much. And the noise level sets in 20 minutes. In contrast, the volatility, which is a measure of the absolute value of the price change. So if the price is changing a lot, the volatility is huge. If it changes a little, volatility is small. And Volatility does have long-range power law correlations. Power law means a log-log plot of correlation function against time is almost straight over almost 3 orders of magnitude. Not quite, but almost 3 orders of magnitude. That's really remarkable, because how could anything be correlated over such a wide range? And notice that the x-axis is in days, so out to almost, not quite, almost 100 days. So a volatile day today implies that 100 days from now, or say 90 days, is more likely to be volatile than not. So there's something complicated going on. This is a complicated many-body system, and people will tell you it's all random, meaning it's all uncorrelated, are simply can't explain this. Because if we're uncorrelated, and all this would be true. Okay, now we have to start talking about trying to understand this. We've used up 20 minutes. So how to understand this? So we look at what really goes on in the trading floor. Here's the trading floor. It's a cover of a magazine you probably saw on the airplane called The Economist. And this is these are traders. Where's my pointer? And my pointer's dying. Oh. No, it isn't. My thumb is dying. So here are a bunch of traders. It's a cartoon. And this trader says to his boss, I got a stock that could really excel. And the neighbor hears the word excel. And then there's a little miscommunication. He hears the word sell. Next, here's the word sell. And the other side, I said, madness, I can't take it anymore. Goodbye. Bye. And this is a cartoon, of course, of the panic, whatever you want to call it, of the interaction of buying and selling. Because if everybody's buying, you tend to think it's a good time to buy. The market's going to go up, and vice versa if everyone's selling. So I like this cartoon. And I also like it because it looks like the icing model, in the sense that these buy might correspond to spin up, optimistic, and sell might correspond to spin down, and there's some correlation between them. And the idea of making an icing model out of the stock market is not new. It's not my idea, but it's okay. So models. So here's the icing model with upspins and downspins, and here's other variants of that. I don't need to go in this. But the key thing that you might find useful, since most people know what an icing model is that there are two parameters. Exchange interaction J, which tells how one stock is influenced by another stock. So particularly if a lot of stocks go down, other ones are more likely to go down. And the second thing is H, the magnetic field, which is like news. News tells you Kennedy was shot. What happened when we found that out? All the markets went down. Boom, 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 boom. And we all know that. So external news is like a magnetic field. It affects all the stocks, not necessarily equally, but it affects them all. So, and of course, it's more complicated than that. So people have played games with Potts models and in-vector models, and I won't belabor this point unless you're interested in doing something new, and you might do something interesting with that. Okay, 25 minutes have passed, so we're on time so far. So I'm going to talk about work with a physicist, named Tobias Price, who wrote me one Thanksgiving Day saying, I'm a postdoc in Germany, but I have Christmas vacation free and I'd love to come work with you. And I told my wife, this guy's very smart. And she said, Christmas vacation? No way. And I wrote him, you really don't have time. He said, but if I come, I can bring a data set, which was every transaction of every stock on the entire German stock exchange. And I got excited. I said, every transaction of every, I said, that's what we want. Because, you know, if you just select and choose, it's like if you're an experimentalist, you say, I'm going to choose these data and these data and these data, and then I'm going to publish a PRL and get a Nobel Prize. No pun intended for Mike. You would say, hey, that's cheating. But he had every transaction of every stock. So I said, come ahead. And so we wrote a PNAS paper, which is fairly well cited a few years back, with Price, with his German advisor and with me. And we call this switching processes, and that's because we all know the market looks like this top curve, and we probably know that if we blow this up and we get something that's self-similar, hence the word scaling, and we blow up again and we get something that looks a little different, and we blow up again, it looks much different, but we all know that there are these switching points. And what the name of the game is to know when these switching points are going to happen. And there's no regularity. They're not, obviously, there's no metronome that says, time to switch, like a dance, you know, when you do square dancing, the caller says, twirl your partner and now switch into a new partner or something. None of that. But we focus on these switching points, and this is a graph of a schematic of the price going down, switching and going up, going down and up. And the volume tracks the price, because when it goes down, traders say, hey, it's going to go up soon, good time to buy. So people start buying. And then if I'm a trader, I see everybody's starting to buy, I say, looks like the market's going to go up, everybody's buying, so I buy too. And then after a while, people, the reverse, they say, and it goes up again. And the same thing happens at the maximum. Time to sell, time to sell, time to sell. So this is the graphical equivalent of that cartoon. It said, buy, 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 sell, 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 sell. They're very much like critical phenomena. Huge. Okay. I'm not sure I need to show you this, but since we're all in the physics department, we've all heard of the Lambda point in liquid helium, which is the point where liquid helium becomes superfluid, and fluctuation phenomena like specific heat have this lambda shape to them. But this is not specific heat, this is something different. This is the transaction volume as a function of time between extrema. And these data are not fit by a logarithm, but very close. The red data on one side are almost a logarithm, the 0 would be a logarithm, and the blue data are a little different. And the time between trades, the same sort of story. They're fit by power laws. So what's important here is not the numbers, because I don't have any idea what the numbers mean, but that the data, even though they're controlled by humans, like my son, he's supposed to have a free will, but he's conforming to this goddamn law. I tease him, I say, you're just a fucking automaton, you know, you just obey these laws. You don't even know it, but you're obeying these laws. Look, your data falling right on this line. So I find this one of the more exciting graphs, even though it's probably ugly to look at, but it's exciting. And here's just what I was referring to. Helium is a critical point. The group of Buckingham in Australia. The only nice thing here, this is specific heat against temperature difference from the transition, the lambda point, on 3 different scales: degrees, millidegrees, and microdegrees. And this just shows the self-similarity. It's called a lambda transition because this looks a little like the Greek letter lambda, no other reason. But since it's self-similar, you get a lambda here, you get a lambda 1,000 times finer, and you get a lambda 1,000 times finer still. So the million times finer, you still get a lambda, as you would. And you would, mathematicians would say, of course, if you have a power law, it looks the same on all scales. Y equals x squared, it doesn't matter the scale. Okay. So, I'm not sure you want to hear this. What time we're 4:30, it won't hurt. So we just saw that the volume peaks and the time between trade dips, and the question is why? And why does all this happen? Where is I said critical phenomena, but critical phenomena is what you get when you start with a bunch of objects like spins, Ising model, they interact with their neighbors or whatever, and then whatever happens depends on those interactions. So where are the interactions here? General Motors doesn't depend on Ford, so to speak. On the other hand, the price depends on traders, and the traders are all interacting like crazy because they watch the same damn screen all over the world. Japan, USA, China, and even the Soviet Union. So as a trader starts to worry to miss the switch and starts to do something, maybe buy or maybe sell, another trader sees that someone's buying and selling, and then there's I use the word panic, like the cartoon, but it isn't necessarily panic, it's just time to act. And so here's the volume again with the lambda shape. Here's the time between trades with the reverse. And these are just log-log plots of those things. You don't need to pay attention to this except to know that when you get a straight line on log-log paper, that means there's some law going on. It's didn't just happen that way. In critical point phenomena, we always got log-log plots with straight lines, and people would say, so what? So what? Another straight line. Everything's straight on log-log paper. I was told over and over for my PhD thesis. My advisors laughed at me, my colleagues laughed at me. But the truth is, when you get a straight line on log-log paper, it means something. It means a self-similarity is the fancy word. And the fact these are approximately straight means there's something going on. And I don't need to show you all this, but other things like volatility are straight. It doesn't matter. But the only thing that might matter is that the range is a factor of 10 to the 9th, 1 billion. Why do I say that? Because you work out all the time difference, the interval difference between the number of seconds in a minute, minutes in an hour, hours in a day, 24 hours in a day, and over 100 days, whatever it was, 100 days, from 100th of a second to 100 days. That's 9 orders of magnitude. So this is, for me, better than critical phenomena. Very few critical phenomena experiments, if perhaps none, are straight lines over 9 orders of magnitude. So when you see something like that, and when I do at least, I fall on my ass. You know, I say, my God, there's something really going on. And the opposite of what I would have thought. I thought every trader is independent. If I do this, and you do that, and you do that, and you do that, good for you. Maybe you'll get rich, maybe I'll get poor, the other way around. But this is a strongly interacting system. Of course, it's all watching the same screen, but it didn't have to be interacting. Okay, I see the time is moving, so I see something a little more complicated, but just shut your eyes if you don't want to hear this. Eugene Wigner is a name we all know in physics from his work in nuclear physics and many other things, but he also worked on something called random matrix theory, which just means a matrix whose elements are random. You might think you can't say anything. That's what I used to think about random walks. If it's a random walk, you can't say anything. But of course, we all know, even undergraduates know, that a random walk has certain properties that are very predictable and always there. And so similarly here, with these crazy uncorrelated, we emphasize, uncorrelated fluctuations, there's something that can be predicted. And what Wigner did, what the hell is wrong with it? Wigner, you don't have to know what this is, but he made a matrix of 1,000 stocks, and each element of that matrix was the change of price of one of the stocks with respect to the other. And then he diagonalized that and looked at the eigenvalues and found a curve. That's a zigzag curve. And then he looked at theory, and there's something called random matrix theory, RMT, that tells what that curve should look like if the things were uncorrelated random variables. And that's what this is, truly random matrix. But as you see, the data are pretty close to that. There are 1,000 stocks, so there's 1,000 eigenvalues, and all but the last 20 or so fit that, but the 20 deviate. And the interesting thing is the 20 that deviate correspond to, each of these corresponds to firms in a given business sector. This might be manufacturing, this might be automobiles, this might be something else. So this is quite, to me, quite remarkable. I have no idea what it means, but it just shows that there's, something's going on. You always say shit is going on, we don't know what it is, but something's going on. So there's things you can think about. And that's why I talk about it here, because you're all bright young people. Not everyone's young, but you're all bright. And so maybe you can figure out what this means. So even more interesting is that the deviating eigenvalues correspond to certain stocks. So this is the same graph, only now emphasizing the deviating one. So this little dashed curve here is the tail of that random matrix theory plot, and here's the 20 or so deviating eigenvalues. And then when you look at the eigenvectors that make up these, you find that they correspond to well-defined sectors, gold and Latin American firms and banks and so forth. So strongly interacting firms give rise to eigen values, I guess, that are similar. Again, what does that mean? I have no idea. So there's lots to think about it. I want to emphasize that because this is a field, unlike so many in physics, where the questions are very obvious, and if you make any progress at all, you could get a Nobel Prize. There is a Nobel Prize in economics, and you're at Brown, where you already have two. You want to make a third one. Okay. Look at the time. I'm not sure I want to tell you this, but let me decide whether to show you this or not. Yeah, I will show this. Okay, liquid water is a love of mine. Ever since I had a sabbatical in Paris and worked in a lab with an experimentalist, and I resolved to write a second edition of a book I'd written as a postdoc, and I never did it because the experimentalist was working on water, and he was finding interesting results that made no sense to me or anyone else. So I started to work on water, and this is a pressure, the pointer, goddamn pointer, yeah. Pressure on the y-axis, temperature on the x-axis of water. And what we know is that what we don't know for sure, but we think the water has a liquid-liquid phase transition at low temperatures, and that line of transition separating one phase from another terminates at a critical point. And the extension of a line of first order transition, I named the Widom line because Widom first taught me about that, but all it means is that there are not infinite singularities, but there are sharp maxima that become infinite at the critical point, but very sharp, and it's easy to measure because there's no hysteresis. So this is a generic picture of a critical point phenomena, and this has been confirmed very nicely by graduate students working with me, Kesselring and Lascaris, and two postdocs, and a colleague, Hans Hermann. And so this is a picture of water, not economics. And this is the schematic. When you do simulations, you can see it. You can see the real balls. And these are the y-axis is the density, the x-axis is the time in nanoseconds, and the system, being near a critical point, is jumping from one density to another density, more than 10% jump. Up and down and up and down in all different lengths. Long time down, short time down, real short time down, and so forth. And if you shine a flashlight from the left and make a histogram, you see that most of the values are either in this higher density, around 1, or the lower density, about 0.9. Now 1, as you know, is the density of liquid water, and 0.9, you probably know from your refrigerator experiments, is the density of ice. And so the water is flipping in its local structure between liquid water and structured water. It's not ice, because ice means infinite range, the ice cube, but it means the local density is like that of ice. So, and the flipping is happening like this as a function of time, at least according to these molecular dynamics simulations, which we said were done by these two brilliant students, and a lot of us holding the ladder. And so why am I telling you this? Because if you, with a little imagination, you could say this looks like the stock market. Market is up, goes down for a while, and pop, up, down, up, down, up, down, up, down, up, down. And if we make histograms, there are good days and bad days. So here is a simulation, not of the stock market, but of water. Why water? Because we know something about water interactions, and they're fairly sophisticated models, and this is probably the best one. And this is going to, every water molecule is color-coded by its local order, where red means, red means disordered region, and violet means ordered region. So this little string of violets are relatively ordered. You can't really see that they're ordered, but they are. But ordered means that the distances from the neighbors are what they would be in ice, approximately, and the angles between them are roughly like that of ice. So this is a snapshot. And now we're going to end this talk on time, time for questions. So gear up with your hard questions. Make a fool out of me. I'll never get invited back. And we're going to look at this for a few nanoseconds. So how do I do that? I do this. There it is. Nanoseconds are clicking away. You see that little cluster broke up right away. And now new clusters are forming. But the important thing is that everything's changing all the time. Even the average is changing. So things are fluctuating, just like the stock market, if you will. You know, this is, you know, the blues are coming back. It's a little like Republicans and Democrats. Now you see the Democrats are coming, oops, the Republicans are coming back. Head for the doors. Moving to England. Republicans are going back. So anyway, this is almost finished. 5 more nanoseconds. So this, of course, it's only a simulation, and it's only a small box, but there's no indication this is not what's really going on. Of course, it's not exactly what's going on, but if you want to think of what water would be like if you had the vision of Maxwell's demon and the time scale of whatever it takes to see nanoseconds, this is roughly what you would see, I think. I hope. Almost finished. Oh. Yeah, we are finished. Okay, so time to say the main message. Data-driven discovery reveals that finance fluctuations are switching without switches, like that last slide. Water switches from one local structure to another, and nothing's making it switch. It just does it all by itself. So the financial markets, people traditionally think, has a cause for everything. You know, somebody coughed and the market went down. Someone dropped their pen, the market went down, or whatever. But it's not necessarily true. If nothing happens, there's still fluctuations. Okay, so it's a good time to ask for questions. I stopped deliberately early, so we have time for some questions. I have time for a sip of coffee. Yeah, ask your question loud enough I can hear, though.
That's very interesting. Can you see evidence of things like collusion in the markets, or
Maybe.
insider
Wow. Never
trading?
thought of
You know,
that.
how would
Never
that?
thought of that. I never thought of that.
You never.
Collusion means, I'm sure you know what it means. It means that you and I agree to do something and don't tell anybody.
Oh yeah,
Is that what it
there'd be
means?
a whole group of us.
Oh, I see. So all of Brown decides to sell General
I'm not going
Motors
to
or
tell you
something.
right, Brown, but you know.
Oh, the physics department. and so you'd be finding correlations, yeah. I don't know, but I mean, obviously, if you're looking for correlations and you see everyone in the physics department is selling the same stock at the same time, I don't know any other than trivial answers to that. But if you certainly, and people look for that. I mean, the authorities that want to catch you for doing naughty things look at correlations among things, and but evidence. So maybe you have some other more precise thing to ask. Collusion. What means?
So the Gaussian is what you consider to be random behavior, and kind of a sign of a lack of interactions.
Yeah.
And in somehow or another, I guess the implication is power laws are actually signaling some level of interactions because it's no longer completely random. And so I'm just thinking about, yeah, are there particular types of interactions you could throw into models? And
Right. So we have a world expert on this subject, Mike Costello, so I hesitate to even answer that. But I think it's fair to say you can have correlations and still have Gaussians, and you can have no correlations and get something else. So I'm not sure the functional, and the reason is correlations say what happens tomorrow, how to depend on what happened today, or what happens in 5 seconds, how to do it on today. And whereas the other thing just says if you're General Motors and I'm Ford, and the auto market is shit today, for me, it's probably shit for you too. Unless they found a mistake in my car or something, in General Motors. And then maybe that's not, but everything's correlated. But we have so many other hands. So where are those other hands? Yeah.
So I have a question about how you
Speak loud enough they can hear you.
How you take into account the general trend. So if I start with your S&P,
Better stay in there, 'cause it's hard to hear.
if I start with your S&P 500 example, the first one, there is a clear trend. I mean, the S&P 500 grows; it doesn't stay constant. So how exactly do you account for that in your model?
I mean, overall time.
Overall, the
That's a drift. That's a good point. So we're studying fluctuations. It's a little like a random walk and have a bias. The probability of left, if the drunk throws a coin that's loaded, say 51% that she goes to the right and 49% that she goes to the left, then there'll be a drift. And after a long time, the cloud of random walkers will move to the right.
Right. So you take the general trend from the actual historical data.
Right.
You only consider the
Right.
fluctuation. Now that brings me.
If we knew how the drift was going, we'd be rich as hell.
Sure.
Because, if you know the market's going to drift upward, then it's the time to buy.
But then what surprised me is that you see this 20-minute relaxation time for this stock, right? And this must be a strong function of time, because 20 years ago, when people didn't have supercomputers to do large volume trading in millisecond time frame, the time constant must have been very different when people were trading pieces of paper rather than computing operations. So I was wondering if you look at the historical trend.
Interesting question. I don't know. I just don't know. So maybe someone else has a thought. But if you have correlations, you can measure them now, because we have every trade is recorded. And you can get these data, by the way. Most universities have access to it. We didn't, but we stole it from MIT at night. And we didn't, but my student did. And he's still not in jail. He's any day now. No, anyway, go ahead.
This is a similarly themed
Be in the mic louder, though.
This is a similarly themed question in that if you see power laws that extend over many orders of magnitude, that looks like a system that has similarity to it. In other words, there's no new physics that's kicking in over many orders of magnitude. But in economics, we expect that at some level it's algorithms, and at other levels there's animal spirits. So
I don't know what that means.
well, that's, I think, Bob Schiller's word for the kind of emotional responses that affect trades. And so it seems like there should be different physics at play at different scales. And what measures do you maybe see changing exponents, changing slopes of these relations?
That's a very interesting question. I never thought about that. I know so little about economics. I know the names you're mentioning, but I don't know animal spirits. I don't know what that means. A girl once said I had animal spirits, but I don't think that's what she meant. Yeah.
Yes, I'm wondering whether there's some takeaways for.
Speak in the mic.
Yes.
I hear you.
Takeaways of, I saw that there's one variable, namely the volatility, which seemed to grow whenever there was a switch coming up.
Yeah.
So that given that the average person has no idea whether the switch is going one way or the other, it might be prudent simply to get into a safe mode when you see volatility going up. Is that a valuable takeaway?
That's a nice point. Very nice point. So when the fluctuations get big, you know they're more likely to have a switch. Very good point. So it's a way to trade. If you measure the fluctuations and they start to get big, something may happen. And yeah, it's a good point. I don't know. I know nothing about this subject. You understand. I just clap my hands so my students do the work, and I give talks at Brown and enjoy good food, but nice people. But I don't understand this at all. I'm not sure anyone does. I mean, people. Go ahead.
There was a graph there that showed the slope of your correlations at 3 versus the one that Mandelbrot preferred. Could you say a few more words about
This one?
the significance? Yes,
This right now.
the Gutenberg-Richter earthquake law. I mean, that's a process. There's random slippages, and there's sort of a driving impulse. Is there, what's the alternate model, I mean, can you say what exactly the significance of that versus the one that Mandelbrot preferred?
What's the that though? Mandelbrot's the top curve.
Gutenberg-Richter earthquake law, why is it, is there some physical model there that is a good model for the stock market?
Okay, good. So that's a good question. So whenever you get a straight line on log paper, to me, I'm a simple boy from Oklahoma, it means that whatever's going on one scale has something to do with what's going on the other scale, otherwise they wouldn't be connected by a straight line, so to speak. So what it means to me is that the big bad things, was my pointer, that are going on at
Yeah, that's the straight lines, but why the slope of 3?
Oh, no idea the 3. You can do something about the 3, write a good paper. Nature will publish it. Nature cares about this stuff. So I had no idea where it's 3. We made a model and everything, but models you get out what you put in, and they're not very realistic. Not like a physical model, where you say this spin interacts with its neighbors and so on and so on. So it's not clear at all. But the 3 is striking, and more importantly, perhaps to me, is 3 for other economies, including economies that are more socialist and less socialist. It seems to be a property of whatever, interacting systems driven by a desire to make profit. I don't know what it's a property of, but a little like critical phenomena, because the systems near a critical point are quite diverse. Material A has exponent, say 3, and material B doesn't look at all like material A, but it has exponent 3. So what the hell's going on? So since they're dead systems, we can say something, if you're smart and intelligent, like Kosterlitz and many others, you can say something about how if you interact only with nearest neighbors, then this propagates order, and the way it propagates depends on the dimension of the system, but not much else. Because in 1 dimension you only go down the Rhine, and 2 dimensions you can spread out like that, and 3 dimensions you go like, and so forth. So what does this mean? I don't know. Is there a meaning to dimension? It's not clear. Nothing's clear. But these are empirical facts that cry out for someone to do something, and you're all very bright here. You're young, you're bright, and there's a Nobel Prize in economics. One more Nobel Prize for Brown, if you can figure this out. Anything to figure this out. Because it's crying out for some explanation. And no one's said anything useful that I know of, or at least that I consider useful. But they're real. I mean, look at many orders of magnitude. On the y-axis is, what do we say, 8 orders of magnitude on the y-axis. That means, and this is the cumulative distribution. So in the PDF, it's 10 orders of magnitude or something. I mean, you take a derivative. So something is going on at one scale and 10 orders of magnitude different, you have the same phenomena. And so if it were spins interacting, we say, of course, because we know how that works. And so there are models of economics that say that firms are like objects, and it's true. And every firm interacts with other firms, that's true. And so you can wave your hands, but the only catch is there's no way to easily quantify that. We don't know how strong. We know Ford and General Motors interacts, but we don't know all firms. And if we did, we might be something useful. I don't know. Might be useful. But it's called business sectors. The business sector starts to get infected by bad news and spills over. I don't know what I'm saying now. So let's take another question.
Yeah. When studying financial markets, in your view, what is the advantage of physicists over mathematicians or mathematicians?
No, just that we're stupid and ignorant. We don't know anything. So sometimes stupid, ignorant people ask questions that educated people would never ask. Or if they asked them, they'd be laughed at by their peers and wouldn't get tenure, or wouldn't get a grant or anything else. They say, I can't ask questions in physics that, that my grant monitor would take away my grant for asking. But we physicists can ask anything we want.
Okay.
So I think, but more seriously, physicists search for simple answers, and economists frequently, not all, say, Stanley, the world is much more complicated. Don't you know anything about economics? You want a simple answer that explains why everything has this slope of 3? You must be crazy. You know, every firm is different. So you can plot one firm, you get 3, another firm, you get 3. I say, well, then tell me why. And they say, I don't know why. So I say, that's my point. There's something universal about firms that makes them all 3. And you can do firm by firm by firm. I have a big average there. I think this is 1,000 firms or some huge number. You know, but 1,000 stocks, yeah. But you can do one by one by one. Of course, this is more noisy, but we did that. We mean my students did that. I have to emphasize, all this work is not mine. It's my students. I don't think I made a single plot in this whole talk. And I tried to identify their names. I think I did at least in this one, the lower left. And I think a useful skill here is willingness to make a graphical representation of anything, because you see the graph tells the story. If you didn't make this graph, who would think of looking for a power law even? I mean, you wouldn't know what to look for. Or because of the rounding of those, you see the open diamonds deviate, but if you didn't have the graph, you wouldn't get a very straight line looking at the open diamonds because it's deviating. But if you make a graph, you can see it's perfectly straight out till a certain distance, and then it deviates. And that's what we get in critical phenomena also. So awful lot about finance is just like critical phenomena, as it should be, because critical phenomena is what happens when a system with short-range interactions gets near a critical point, which means that the system is tuned. I don't know what I'm saying. Never mind. I'll stop the sentence.
Can I ask you another question?
Yeah.
That is, when you study different random systems, right, like a weather, earthquake, they have no feeling, but the stock market, right, there's immense of human psychology and irrationality.
You think so, but my son is not irrational. He'd get fired. He's very rational. In other words, you don't, it's true that there's some irrationality, obviously. And, but I don't think this is the main thing. It may cancel out too. One person loves stocks that begin with the letter A, and another likes stocks that begin with the letter B. It doesn't mean much. No. But you're right. I mean, the human factor is missing here. I didn't refer to humans at all. But we also know many properties of humans are straight lines on log paper. Again, as if people have to conform to some ridiculous law. And laws of many things, of income, for example, Pareto's law. No one's telling you, you can only earn so much because he earned more and you can only earn that much. Of course not. It's a strongly interacting system. So something's going on, we don't know what. So that's why I'm excited about it. And, you know, hopefully in 10, 20, 30 years before you guys all retire, there will be some big progress, or maybe not. No one knows. No one knows. More questions? Yeah, Professor Costello. You need a mic.
Have you got any idea what properties of, say, the stock market are due to anything but central limit theorem?
What did you say? Due to elephant?
No, a lot of the properties of the stock market, as far as I understand it, are just consequences of things like the central limit theorem.
It's 17 hours.
Is that me? Okay, central limit theorem. Yeah, but that's yes and no, because central limit theorem makes Gaussians, and nothing. I mean, almost nothing is Gaussian. So.
Well, there's one example I know of. It's called Benford's law.
Benford's law.
About,
tell them what Benford's law is. Sir.
Which I learned about it from Cardar's book on statistical mechanics. And that is a hard prediction, which is verified by observation, based on the central limit theorem. You know, it's not a very important observation, but if you want to know what fraction of the stock prices, you know, stock prices begin with 1, what's fraction begins with 2, and so on and so forth, this Benford's law gives it to you spot on. And that's just an exercise in the central limit
What's
theorem.
the point of that statement? Do you know what Benford's law is? Someone named Benford looked at numbers, and naively you would think the first digit should be random. You get as many ones as you get twos or threes or fours. But in fact, he found not true. And as Mike just said, he found that there was more with ones, right? And more ones than twos, it was twos than threes, and so forth. And so that named after him. Is there a good explanation for Benford's law yet? I know there are many explanations.
The only explanation I've seen is that if you assume that stock prices are a product of a large number of random variables, it falls out. That's the
Benford's
only
law
input.
falls out, but not these laws.
Sorry?
Do these laws fall out?
Not these laws, but
No,
Benford's law
I'm interested-
follows.
I don't care about Benford's law. That's Benford. I want Stanley's law.
No, so what I was asking was, I'm just saying that many of the,
Yeah.
some of the properties, at least, of stock prices is due to large numbers of properties of large number of random variables. But what properties are significant, if you see what I mean?
It's a good question. And that's a very good question, it's a little like what we ask in phase transition critical phenomena. We know that near the critical point, all hell's breaking loose. Everything's fluctuating like crazy, and energy fluctuates, and magnetization fluctuates, and so forth, and the clock is fluctuating near 5 o'clock, so I'll speak a little bit faster. But what's really going on is not so clear. And then some smart people, at least one of whom is in this room, and many others, of course, began to realize that some things matter more than others. And that's what we're not at that stage now, I don't think, in finance. Maybe, I don't know.
I guess
Give him the mic, I can't hear him. Yeah.
I guess the motivation of the question is, how do I get rich from the stock market?
If you find out, please tell me before anyone else.
Okay.
You're so smart, why aren't you rich? If I can conclude with a joke, an economist meets a physicist on the train, and they do blah, blah, blah about their work. Each a little bit impressed with the other, so the physicist says, the economist says to the physicist, if you're so smart, why aren't you rich? And the physicist shoots back, if you're so rich, why aren't you smart? Which of course is not fair, because of course economists are very smart, but I can only tell that in a room full of physicists. Okay, thank you all. You used up my hour. I invite you all to Boston. I said already once, but I mean it. Give me a little warning if possible. If you don't give me warning, I may say no, but otherwise I'll say yes. No.
Take the mic off now?